Thank you very much for coming. So yes, we will be talking about R values. I titled the talk is C++ R value lifetime disaster. Well, you'll see why I think it's a disaster. Let's talk just about R values for now. So why do we have R values at all? In particular, R value references, that's what I'm talking about. It used to be that we wouldn't have R value references, and there was the standard library, and the standard library really likes value semantics. And value semantics means that values are independent of each other, you can pass values around and they keep the value. But if you do that with the old standard library, and that was before C++11, I don't know how many of you already programmed C++ before C++11, back then it meant that you needed a lot of copying. So whenever you would put something that is a vector, for example, and you want to put that vector into another vector, you would have to copy the whole content of the vector into wherever it should go. And that means you need to copy data, you need to allocate your memory, and that was all very inefficient. So basically the C++ community said that cannot continue. We need some idea that makes that whole thing more efficient. And this is how R value references came about. And this is a typical example. You have a vector of vectors, and you want to put another vector into that vector of vectors. And that vector already has memory allocated. And when you put that vector now into the vector of vectors, then you don't need to reallocate the memory. You can put that magic just move around it, and then the resources of the vector get moved. So they get basically removed from the vector. You end up typically with an empty vector, and the destination vector gets all the content that the original vector had. Now, that's one usage for R value references. Once they had been invented, there was actually another usage for them. R values are things which are not variables, typically not variables in your program, but they are just expressions whose value goes away pretty soon. That's why you can actually steal resources, because things that go away anyway, well, you may as well take away the resources because you won't need them anymore. But that also means that R values tell you something about the lifetime of a variable. And that was already used back when R value references were introduced with a little bit of in an obscure utility that's called, that's the cref. Cref was to wrap references for defined expressions. Both not used terribly much anymore, but for the upcoming C++20 ranges, the whole idea of R values and the lifetime, that information that is associated with them, becomes a whole lot more important. Now, I don't know how many of you are familiar with ranges. Hands up, anyone who knows ranges already? Okay, not that many actually. So, short detour about ranges. So the new C++20 standard will have an alternative implementation of the standard library that doesn't use iterators anymore. Instead, you kind of put together a pair of iterators into what's called a range. And because the pair of iterators, they really belong together. And the interesting thing about ranges is that you cannot only use them to iterate over data. What you can also do is you can basically take that range and adapt it lazily. So you can say, okay, I have that vector here, and this is the example, I have a vector of ints, and I would like to remove all the odd elements. I would like to keep only the even elements. And I don't do that by modifying the vector. Instead, I'm creating a new object, which when you iterate over it, it will just skip all the odd entries in my vector and keep only the even ones. And this is a very powerful tool, very similar to what you do in functional programming. And in our code, we already use it a lot. We have our own standard library, our own range library that you can find on GitHub. And there will also be one in C++20. And what's important is when you are putting in this expression like it's written here, then the object, as I said, will be one that you can iterate over. Have a begin and an end, and you can get iterators from them, you can iterate. But it is really just remembering internally a reference to the vector that it's filtering, or whatever it is filtering, and the filter function. And when you iterate, it will lazily execute that filter function and give you the elements that are left over. Well, the important part here is that that object references the range that it's filtering by reference. So it has to stay alive. If your vector goes away, dies, you end up with a dangling reference inside that object RNG here. And to prevent that, the C++20 standard library will not allow compiling an expression like that if the filtered range, the vector, is actually an R value. So it is actually suddenly now important whether something is an R value or an L value. And before we talk about these lifetime or these implications that this lifetime information has, let's talk first about how we use range, how we use R value references for moving. Okay, that was the original usage for it. And that's already a little bit tricky. All right, so if you look at this piece of code, probably many of you, well, who thinks it's good? Who thinks it's bad? Come on, arms up. Okay. All right, so what's bad about it? Well, it's bad in quite a few ways. So your intention would be that A gets moved, that you don't have to make a copy of A, that your resources of the A get actually moved. And this doesn't work. Why doesn't it work? Well, your A is const, and you cannot move out of const, which is, it's not quite so intuitive. If you know how it works internally, it's clear, but for a beginner, that's not so clear at all. So, well, what do we need to do? Well, we need to remove the const, first of all. So it's now good. Who thinks it's good now? Who thinks it's bad? Okay, why is it bad? But there's a std move, right? So the problem is, here, the std move works. It will move the A, but we can actually do better. If you write it without the move, like here, then you get something called the main return value optimization, which, basically what happens is that the A originally gets allocated not in the stack space of the function, but instead in the place where the return value will go. Because the compiler can find out that you're always returning the same variable, and it can place it in the right place right away. And then you don't really need a move. And actually the move makes things worse, because that kind of obscures for the compiler that you want to do this return value optimization. Okay, what happens here? Who thinks the code is good? Who thinks the code is bad? I'm not so sure, huh? Yeah, code is okay. Well, it's confusing, but this NRVO actually works with const objects. Move doesn't, but NRVO works. It's the return value optimization. All right, but let's say you have two branches inside your function. Okay? Now, what happens with your NRVO? Your NRVO doesn't work anymore because you don't have a single variable anymore that's returned, and the compiler won't actually know where to allocate the variables. There's only a very specific case where the compiler is allowed to do this optimization. And you get a copy again because you have a const. Okay, so putting in the const on variables that you want to return is kind of dangerous. If you really understand what you're doing, it works, but if you later on refactor the code and you have a different return path, it doesn't work anymore. All right, so what happens now if you remove the const, you get a move. Okay, good. Now you think the game's over. No, not yet. Another thing, okay, you have a B that aggregates an A. All right, so you allocate the B, and you return then the aggregated A, the member of B. Who thinks the code is good? Depends on what?
If you want to get the reference
I want to get the value. I want to return an A. Foo, it's an A foo.
I think it's good.
Okay, you think it's good? No, it's not good. Copy. The return value optimization doesn't work, and it also the kind of automatic R-value-ness of a return doesn't work. So the members of things that when you return a member, it does not become automatically an R-value. So what you have to do is you have to write still move around it. Completely intuitive, right? And you don't have to write it around the whole expression. You don't have to write the move of b dot ma. It's enough if you move the b, because indeed member access of R values, these are R values. That's okay, and they get moved automatically. All right. So I think now we're done with that moving. Next topic. Say you have a structure A, and it's again embedded in a B. And you don't want people to access the A directly, so you have an accessor function that returns the A by construct. And outside you have code that takes that A from B. Okay, so far so good. So you have a construct that gets passed out, and A is an A construct. Good. Now let's say we have also a structure C, and that C also passes out an A, but that time by value. And you have code where you don't know. It's generic code. You don't know whether you get B or a C. You don't know whether the thing that you have returns the A by reference or by value. And I'm writing this. Auto construct A equals either B or a C. I don't know. Get A. Good or bad? Who says bad? Who says good? Not so sure. Okay. It's okay. Thanks to this magic temporary lifetime extension. Temporary lifetime extension is something that was around long before there was auto and long before there were R-value references. It's this ugly corner of C++. That kind of, the idea is nice. The idea is you always write constructs, and it kind of automatically works. Not bad. Let's see. Let's say we have, again, this structure C. And we always have the structure B, but the structure B is not really that interesting. Let's say we have that C that returns by value, and we want to take by construct. But now we have a choice of two A's. Either we take the A of C1 or the A of C2. And we have a less operator to find an A, and we take the minimum one of the two values. Does that work? Who thinks it's good? Who thinks it's bad? Okay, a few more hands that say it's bad. It is bad. Well, to understand why it's bad, let's look at the implementation of stdmin. Stdmin is kind of new. I would even say it's broken. It takes the parameters by construct. So whenever you pass something to it, it tunnels through this construct. And the get A that was an R value turns into an A construct, an L value reference, and gets returned. So that auto construct that you write in front of the stdmin doesn't even have a chance to recognize that this is anything but an L value reference. So you get a dangling A. How can we improve that? Well, first of all, we need to improve the min. Okay, we need to pass the information out that we plug in. Let's do that. Now with C++11, of course, we perfect forward everything. So let's perfect forward for min. Okay, so we write an our min that takes left hand side and right hand side by universal reference, and then forwards either one of them out. Okay, so in that case, the our min actually passes out correctly the R value reference. All good. All right. Well, the problem is A still dangles. It still doesn't work. Why doesn't it work? Remember, temporary lifetime extension is something that they put into the language a long time ago. And R values weren't around definite. And they didn't really update or think about much of the consequences of R value references when they introduced them on temporary lifetime extension. Some things work, some things don't. And this is one of the things that doesn't work. If you get an R value reference, then there is no lifetime extension. This is kind of understandable because the problem is harder than with actual values that you pass out. With values, there is actually a value on the stack, and all the compiler needs to do is to avoid destroying that value. Now, if you're passing an R-value reference out, I mean, a reference is still a reference. It's a pointer out somewhere, right? So the compiler will need to generate a copy underneath somewhere and preserve it, and it doesn't do that. So temporary lifetime extension and R-value references don't really work together. Now, before we look at an alternative, let's look at some other problems. Say you have a function foo, and that kind of is designed to return whatever sum A returns. Sometimes sum A returns value, and sometimes it returns reference. If you return anything, you just want foo to return the same thing as sum A. Okay, and if you don't do anything with the A, it's actually quite simple. You just say, right, return sum A, and you have to write deckel type auto, and everything works. Everything is configured. Now let's say you want to do something with the A in between. Okay, so we take the A, and we do something with the A, and we return it. Now, how does the function have to look like in order to make that work? Well, one idea would be, well, let's take the idea of temporary lifetime extension, because I mean sum A is either a value or a reference, so we do temporary lifetime extension so that we are flexible, and then it looks like this. So you take all the const A, sum A, you do something and return A. This doesn't work because even though you invoke temporary lifetime extension, the A for the type system is still a const reference. And if you return it, all it does is it's returning an auto const reference. So you just delay the pain. You don't have a dangling A immediately. Instead, you have a dangling A returning from foo. You don't have the dangling A when it's returning from some A, but from foo. Not great. Alternatively, we could say, well, what if you don't return deckel type auto from foo, but return auto? Well, yeah, that works, but that always generates a copy. So that's also not really what we want. So what do we want? Now, the real problem I see, and that's why I think temporary lifetime extension has to go. It should be deprecated, and don't even think about it, don't even use it. Is temporary lifetime extension is lying about its type. If you, whatever machinery you have in place to reason about type will break, because temporary lifetime extension tells you it's a const reference, although it may very well be a value. And values die at some point. When you go out of scope, they die. And the lifetime extension is hiding that from you. That's kind of neat. I think deprecate it. Don't use it. Forget about it. What we really want is we want a variable that is actually a value when it's filled with a value, and it's a reference when it's filled with a reference. And that's not lying to us. If you ask it, what's your type, it should give a truthful answer. Well, I tried to build this using an ugly macro. It's a macro, it's ugly, I know, but couldn't do any better. So what do we really want to do here? We want to decay R values. Whenever you're getting an R value, either a value or an L value reference, we want to decay, we could turn it into a value. If you're getting an L value reference, we leave that L value reference alone, we just take it as an L value reference. And that is what the type function, this decay R value is doing. And then we wrote it in a macro that determines the type of our expression and generates the correct variable type, and then uses that actual variable type and assigns the expression to that variable. Okay, and I called it auto-cref, and we use it. Well, let's look at some of the properties, whether this fixes some of our problems. If we use the auto-cref with now the foo, with deckel type auto, it will actually work, because now A is either a value or a reference, and we're returning the deckel type auto. So, and that basically returns whatever the type of A is. Watch out though, C++ wouldn't be C++, and there wouldn't be any more pitfalls. Don't put any parentheses here. If you put parentheses there, then the type that is deduced by declaration type auto will be the expression type. And the expression type of A at this particular point would actually be a reference. The declaration type of A itself is actually the declaration type of the variable. So I don't know why they call both declaration type. They shouldn't really. And the one is the variable type and the other one is the expression type. But all right. And we use this a lot. Auto-cref is great. We use it everywhere. It works automatically. You don't have to think about much anymore. By experience, it's good. It works. You get efficient code, and things don't dangle. If you write the rest of the code written reasonably, then it's nice. We use it a lot. There's one little detail. If you want to move out of if you assign a reference, then you get a const reference out of this thing. So it's const. If you assign a value, so far we said it's a mutable value, which is kind of inconsistent. And the problem is that we need a value to be mutable in order to move out of it. So we kind of can introduce two flavors of the auto-cref. One you want to move out of, which is either a mutable value or a const reference. Or you don't want to move out of it, then you make it a constant value and a constant reference. And we have both of these flavors, and if you want to make that distinction or not, well, I'll leave that up to you. So let's see whether that also fixes our minimal problem. So you have our min, we have already fixed that it returns an R value reference, and then we assign it to A, and actually works. So our min returns the R value reference, and the auto-cref then returns this R value reference into a value, and we get the right result. Great. So let's see what C++ is doing with these R values. Let's say you have that kind of code. You have an A, and again the A is embedded in a B, and you generate a B, and then you get the A out. Not so unusual. Well, and I'm using again our little auto-cref facility to get around these other problems. And actually it works, because the declaration type, the expression type of the R value dot member is an R value again. We had that before. So A turns out to be a value, and you don't get anything dangling. All good. But let's say the MA now is public, right? You usually don't have things public. You have accessor functions, and because you don't want people from the outside to mutate your variable, so you write an accessor for them. So the variable is private, and you have a public accessor, get A. And you write the same code, kind of. Instead of MA, we write get A. Does it work? Yes? Arms? Yes? Arms? No? Okay, no, of course not. Because it's a const ref. And because the get A returns an a const ref, so our auto-cref doesn't know what to do with it anymore. So you get a dangling A. No good. So maybe I can improve it. I put an ampersand after it. That's kind of indicating that you want an L value reference, right? Only L values are allowed as a caller. No. Constref, if you can write constref after your member function, or you can write const after your member function, it's identical. It doesn't matter. Just a newfangled way. I don't know exactly when it was introduced, 14 or 17. But you can now write after your constant member functions, you can write constref, indicating kind of that this object is taken by constref. It should be indicative of what you're doing. But that doesn't change the fact that the constref binds to anything. It will bind to R values, it will bind to L values, to anything. And it doesn't matter whether it's a member function or a function parameter, it just binds to anything. So strictly speaking, any constref accessor you have in your code that does this is broken. It's broken because it produces dangling values when you access it on an R value.
Not good. I call this think cell the C++'s R-value amnesia. This binding you bind to constref, and R-value is gone. We forget about it. And there are interesting facts in the language, which are kind of indicating that the people who design the language recognize that there is a problem. Let's say you have a function L that returns an L-value reference and a function R that returns an R-value reference. And say you have a ternary operator that decides between two L-value references. What you get as a result is, of course, an L-value reference. If you decide between two R-value references, what you get out is an R-value reference. So far, no surprise. What if I mix the two? If I decide between an L-value reference and an R-value reference, and you have to come up with some sort of common type. Okay, so what's that common type? What's the type of that? What's the decal type? False, question mark, RL. What's that? Is it an L-value reference? Hands up for L-value reference. Hands up for R-value reference. Okay, we have more R-value reference than L-value reference, which is a good intuition. Of course, it's wrong. But who thinks it's something else? Yeah, it's something else. It's a const. Why a const? I don't know. Because they were probably afraid. They were like, oh my god, if like this thing goes out of scope, and then we have to get dangling, and it's like, you make it a value, make a copy. Come on, make a copy, and then we are on safe ground. Let's make a copy. Okay? Yeah, that's C++. All right. Ha! There is a new kid on the block that kind of has similar functionality. That's common reference. Now, this comes about because you have C++ ranges, C++20 ranges. And what you can do with these ranges is things like merging two ranges. So you can have, say, one sorted range and another sorted range, and you can have an adapter that puts these two together into a sorted range that is kind of lazily sorted. It will grab elements from one or the other range while you're iterating over it. It's an adapter. It's referencing one range and it's referencing the other range and iterating through both of them at the same time. Now the problem is both of these ranges obviously have iterators, and these iterators have, when you dereference them, they have return types. So when you call star it, this will have some return type. And the one will have a return type, and the other will have a return type. So you have the task, naturally, to come up with a common type, a common reference. Because you have two references. The iterators typically return references. And so you need a common reference. This is a bit like common type, what we also have already in the standard. But a common type is always a value. This one is not. This one can be a reference. Okay, because that's what we need for the iterators. So we play the same game. We decide between two L-value references, and you get an L-value reference, and you decide between an two R-value references, you get an R-value reference. And you decide between an R-value reference and an L-value reference. What do you get? An L-value reference. He's happy. He's like, oh, that's fine. That's okay. Just make everything on an L-value. So just forget about R-value-ness. Come on. It's not that important. Right? Come on. Okay. What if I make one of them a value? A const and a constref. That's an A. I don't know. It's an A. I don't know why that lifetime is different and why he decides to make a copy in that case, but that's what he decides. Okay. Anyway, so common reference really likes R-value amnesia. It's like, R-values, come on, forget about it. Okay, now I complained a lot, right? I complained about all these things that don't work. Now, the question is, what's correct? How should the world be? Like some wishful thinking. Something like, well, okay, how can we solve this mess? Well, let's look at the world of references. There are const references and non-const references, mutable references. And there are R-values and L-values. L-values have typically a long lifetime, and R-values have a short lifetime. And some are mutable, some are not mutable. Now, if you look at what currently C++ allows in terms of conversions, one more attribute actually, because the R value is mutable, when an R value is mutable, you think it goes out of scope. So you kind of claim that you can scavenge from it. You say, okay, you can take away its resources, it doesn't matter so much. So that's an extra property you have for R value references, only mutable R value references. All right, so now we look at what C++ currently allows. These are the conversions that we currently have. So an L value reference can turn into a const L value reference. The R value reference can turn into a const ref and to a const R value reference. You cannot turn an L value reference into an R value reference. It looks kind of okayish, but the problem is that you would scavenge resources from it. You would break that L value reference. That's why we cannot allow this. But what you can see from these arrows is that there are two arrows pointing from a short lifetime to a long lifetime. This is exactly that R value amnesia, where things just turn into L values for no good reason. In order to fix this, we need to turn the arrows around. Right? So we can only go from long lifetime to short lifetime. We have to weaken the promises we make. If we can always make the lifetime shorter, that's fine. We can always make it less mutable. We can always go to const. That's safe. And we can always go away from you can scavenge from this thing to you cannot scavenge from it. That's fine. Right? But we can't go the other way. That makes promises that they cannot fulfill. And from that diagram, you can see that only L values really should bind to const ref. And this ugly duckling that no one really knows what to do with it, the const ref, that's suddenly our weakest reference. That's the reference that anything can bind to because it doesn't make any particular promises. So, yeah, it's so sad. It's so sad. C++ is broken. Okay, and yeah, I'll make an attempt to fix it. Now, big disclaimer: this has not been implemented. This is just an idea. This is just basically to say there is hope somewhere. We could potentially do this. I think maybe we can do this if someone sits down and writes a Clang implementation that does it, tries it out on millions of lines of code, and then can stand in front of the committee and say, hey, I tried it. It's not, we can do this. It's fine. You guys have experience with it. It's been on GitHub for eons and it works. Okay? But none of that has happened yet. I'll still tell you. Of course, existing code must continue to work. We cannot ever break existing code. Even existing libraries must work with the new code. So you have to be able to write new code and not only link to existing libraries, but I would say you have to be even able to use existing headers, because there are header-only libraries out there that you want to continue to use. So we have to be able to gradually introduce this new binding behavior. The rules of the game are going to be that any reference you declare either has the old binding behavior or the new binding behavior. This is not quite so obscure as it may sound, because binding of a reference only happens at the beginning of its lifetime. You cannot change what a reference binds to. It's binding, and that's forever. And once it's bound, the type is going to be the same as before. So when you have once you're using just the reference, it's fine. No change to the behavior is going to occur. So I'll just say, okay, you can just pragma this new binding behavior on and off. You can just say, I'm going to switch it on, I can switch it off. And whatever is actually declared inside that pragma is going to obey to the new binding behavior, even if you call it from the outside somewhere. So just to jog your mind of where everywhere these references are declared, let's go through the places that I came up with. And I don't know if the list is complete, but if you have another one, let me know. But here's the list I came up with. So first of all, of course, you have global and local variables that you're declaring. Typical variable somewhere in your code. You have structured binding, which creates variables. You have parameter lists of functions and lambdas. They can contain declarations. You have aggregate initialization. You have initialization in a constructor, your plain vanilla constructor, and you have lambda captures. And that's pretty much all I could come up with. Now, in all these cases, you could imagine that wherever this statement is written, we assign new binding behavior if it's inside this pragma clause. I think it should work. Now, how would that look like? You have you declare an A that takes an int constref outside of our new binding. Now you declare a B and a C inside new binding, and now we want to define B. Well, that will probably be a compiler bug because the B is kind of defined outside of your pragma clause. So the B is old behavior with constref where it's defined, but originally it was declared somewhere with the new binding behavior. I imagine this would be kind of by file. You would say, okay, this whole file, all the new code I write is going to be new binding behavior, but my headers up there are going to be old binding behavior. Okay. So the A5 would compile because it's old. The B5 wouldn't compile because the 5 is an R value, and R values don't bind to constref. But C5 is fine. We declared it with an R value reference. Okay, so 5 can bind. And when you call the C with an L value, right now this wouldn't compile because the constref cannot bind to L values. In my world, it could. Okay. So I thought about, okay, what kind of impact would that have on the standard library? I think it wouldn't be so terrible. Of course, we probably would need some feature test macro. And functions are kind of equivalent. Once the declaration of a function is written, it does what it does. It either takes L values or it doesn't take L values, R values. So it's the behavior wouldn't change. The only thing that where I could imagine it makes a difference is when you calculate the common reference. Because there, you kind of have to take into account whether what you are passing into the common reference has the new binding or the old binding behavior. So whether you basically, when you pass in a constref and a constref, are you going to get a constref out, or are you going to get a constref out? I looked through all the traits, the type traits, and looked at whether there's any other impact. Couldn't find any. Okay. Of course, this is all future, and we don't have it, and we'll probably never have it. And this is sad, but yeah, and that's how the world is. And anyway, what can we do until then? Well, first of all, let's get rid of this temporary lifetime extension. We wrote AutoCref, which works beautifully. We use it in literally a million lines of code, and it works. It does have currently the problem. I don't know if I mentioned it. It does have the problem that in C++20, it doesn't work when the expression contains a lambda, which is kind of annoying. But C++20 will make this problem go away. You can write a decal type on the return value of a lambda, and it will tell you the proper return value. So it's okay. Now, the member accessors, we again wrote macros. We say, okay, every member accessor you write has to delete the corresponding R value accessor, so that you cannot call it on R values. You could make different decisions. You could say, okay, I'm going to pass out MA as a constant R value, but we didn't do that because maybe you want to scavenge, but you cannot really mutate internal variables. Maybe you break some invariant in the class, and so the easiest or a cautious decision was to say, okay, I'm going to disable it for R values. The common reference can be fixed. You can write a common reference that doesn't have that bug. So basically what you do is you calculate the regular common reference, and then you check if my common reference that I have, if that's an L value, and somewhere among my list there is an R value, that's bad. And then we just make it an R value reference. Right? So we just fix the particular problem we have. And if you want to do it, now you may think, well, what is that all good for? Does it help me in practice? Well, actually it does. So say you're using these ternary operators. Right now it's a const. We had that already. If you write that with our new common reference that we just implemented, and again, we have a macro, that is basically wrapping this, is this new ternary operator, I call it conditional, then if you use that new ternary operator, things like, you know, the conditional of right and left actually generates an a-const reference, an R-value reference. The advantage here is you don't get a copy. C++ would force a copy on you, but you don't really need a copy. You may not want to copy because it's costly. So if you just use that function, then you won't get it. All right, so that brings me to the end of the talk. Constref should never have bound to R values. And fixing C++ may be possible. I think it would be possible in my ideal world. I'm an experimental guy. I would like to do it, but we need a clean implementation. And there are tons of people out there who probably have huge objections of doing such a disastrous thing. And it's probably not going to happen. And until then, we have to get by with mitigations. Thank you very much.